Chapter 5, Aerodynamic Modeling Guidelines. First, we're going to talk about the aerodynamic basic coordinates. The aerodynamic basic coordinates system of ZONAIR must be at 0 angle tack and 0 side slip angle. The fuselage must be along the x-axis. If the configuration is symmetric about the XE plane, only a half-span model is required, even at the asymmetric flight condition, like you have a alpha and beta. The ZONAIR internally will decompose the asymmetric flight condition into a symmetric flight condition and anti-symmetric flight condition. Then you will use the so-called symmetric ASC matrix to solve for the symmetric flow solution, and using the anti-symmetric ASC to solve the anti-symmetric solutions. At the end, ZONAIR will superimpose the symmetric solution and anti-symmetric solution and give you an asymmetric solution. However, if you want to use the CAV or wind tunnel measure CP to replace ZONAIR computer CP on the rigid aircraft, in this case, you have to model the full span model. The flight condition of is specified in terms of a free stream Mach number and the angle tack and the side slip angle and the roll rate, pitch rate, and yaw rate. Okay, so the pitch rate and the yaw rate is followed by the right-hand rule. So it rotates about the x-axis and rotates about the z-axis. But the flight dynamics people's coordinate is the x going forward, the z-axis going downward. So the sign convention of the roll rate and the yaw rate between ZONAIR and the flight dynamics are opposite. Okay, and also the rolling moment and yawing moment computed by ZONAIR, the sign is opposite from the flight dynamics people. So if you have a C and beta, like the yawing moment due to side slip angle, because the yawing moment is about the z axis, so the sign between C and beta computed by ZONAIR and computed by the flight dynamics people are opposite. But however, if you want if ZONAIR calculate, say the rolling moment due to roll rate, because the rolling moment the sign is opposite and the roll rate also is opposite from the flight dynamic people's sign convention. So the rolling moment due to roll rate, the resulting sign is the same as the flight dynamics people's sign convention. For the wake modeling and for the thick wing model, ZONAIR needs to put you need to put the C-bars along the upper surface and lower surface along the trailing edge of the wing. And for the truncate end body, you need to put the C-bar around the end of the body. So the potential difference between the upper and lower surface of the wake is constant. Thus the potential on the upper surface wake is equal to the potential at the grid point at the trailing edge of the upper surface wing, and this potential on the wake along the lower side is same as the potential at the grid point at the trailing edge grid on the lower side of the wing. And then if you have a coplanar wing tail configuration, and then if both wing and tail are modeled by the thick wing, also you have a flat fat body here, and the wake from the wing can penetrate into the body and can penetrate into the tail. So this weak penetration problem will create a singular AIC matrix. To circumvent this problem, you have to use the weak net and to create a curved wake to avoid this weak penetration problem. But later on, we're going to show you a case if the wing and tail, they are not exactly on the same plane, so only the partial wake from the wing wake penetrate into the tail, and there is a way to avoid this wake penetration problem. And when wing sustain lift, flow can separate at the tip of the wing and along the leading edge of the swept wing with sharp leading edge. This separation produces wake sheet that roll up into strong vorticities and sending to downstream. And the studies of a principal wake indicates the wake roll up shape and the strength are relatively independent of the vorticity and can be modeled as potential flow. And two types of roll-up vortex can be modeled in ZONAIR. First, you're using a vortex element, line vortex element modeled by C-rod, and another one is the vortex roll-up sheet by Vortex. And if you have a wing body configuration, and when the wing generates the wake surface from the trailing edge of the wing, then you have to put a C-rod along the wing tip to have a closure to satisfy the closure condition. And however, if you put a C-rod along the inboard of the wake, this is incorrect modeling because the flow cannot roll up from the wing root, and so you have to satisfy this closure condition by adding influence line vortex along the free edge. But this C-rod is physically unrealistic because the wave cannot roll up at the wing body junction. The correct modeling to satisfy the closure condition is to use the RBE2 cards that automatically generate a set of C-bar elements along those grid points on the body behind the wing trailing edge. These C-bar elements serve two purposes: to fill up the gap so that the closure condition is satisfied, because each C-bar will internally sweep down to the infinity and create a wake surface. So those set of C-bar elements can fill up the gap. And the RB2 also internally separate those grid points on the body into a set of a grid along the upper side and another set grid along the lower side. So actually you have two sets of wake sheets generated by those C-bars. And the potential difference between those wake surface so you can impose the potential jump condition due to the wake at those body grids, so that the potential jump is continuous from the wake to those body grids. So you have a potential jump due to the wake from wing. You have the potential jump due to the wake from the C-bar, and those potential jump are continuous. And so if the thin wing modeling is achieved by using the CO7 card, so you have the wing, you have the tail. If they are on the coplanar and then it's better to model the tail using the CL7, because in the computational domain, CL7 is a flat sheet of surface, so it does not have the so-called wake penetration problem. And also another case, if you model the wing by the thick wing modeling, you use C4 and C3 to model the wing in supersonic. And in the supersonic, and we have a so-called Mach cone. The Mach cone is the angle of the Mach cone is equal to the arc sine of 1/m infinity. Okay, so when the Mach number increases, the cone angle decreases. So if you have a wrong leading edge, okay, you can easily encounter so-called super inclined panel, because if the Mach cone cuts into the panel, this panel is called super inclined panel. So in this case, we also recommend you to use the thin wing modeling, because the CL7 in the computational domain is a flat sheet. Okay, then we place the linear chorus source to simulate the thickness effect of the wing, and we put vortex along this flat sheet of surface, and to generate the lift. And the CL7 Bokta car is a macro element. First, you will divide the CL7 into many strips, and then you will further divide each strip into many chorus panels, and you will place the control point on each panel. And because so for supersonic aircraft, in order to avoid the super inclined panel along the wing leading edge, it is highly recommended that the wing horizontal tail, vertical tail be modeled by the CL7, which is the thin wing modeling. And however, if you have a wing body junction, because each CL7 only can model a trapezoidal like shape, okay, so the inboard and all the root and tip of the CL7 always parallel to the x-axis. But if you have a non-constant body, then there will be a gap. So first of all, you cannot insert the CL7 into the body. The CL7 must be outside the body. And in this situation, you have a gap between the root of the CL7 and the body. So in the CL7, there's attached entry. Once you say this is attached to the body, then ZONAIR will create so-called gap panel to fill up the gap. But the leading edge and trailing edge of the gap panel is parallel to the XZ plane, and if you don't follow this rule, otherwise the aerodynamic influence coefficient from the gap panel may create a large error. For a wing root attached to n number of grid points on the body, such as grid I to 1 to n, then you have to use the following equation to calculate the RCH, which is the wing root chord in the CL7. So RCH must be this x location minus this x location. And how do you cut the wing root into chorus panel? You have to specify A effect cut. You have to use this equation to calculate the value of the A effect cut we refer to by the CL7. And the thin wing modeling, on each strip of the CL7, we put the linear vortex linear chorus doublet. Based on the Stokes theorem, the linear chorus doublet is equal to the constant vortex vector. Okay, So because it is a linear doublet along the chloride, so the line vortex along the leading edge and the trailing edge between adjacent chloride panel, they cancel out. So you don't have the line vortex. However, the doublet distribution between two adjacent strips, they are not continuous. Therefore, when you create when ZONAIR convert the linear chloride doublet into vortex singularity, and you will have a two-line vortex along the inboard and outboard of each strip. And so there is two line vortex generated from each strip. Because and also on a weak surface, because the vortex strength is mu x, and the delta Cp between the upper and lower surface of wake equals to -2 times mu x, and the delta Cp on the wake on the wake is 0 because the wake cannot sustain force, and so the vortex integral is only evaluated on the surface. You don't have to model the wake. So whenever you specify CO7, you don't have to worry about wake because wake influence is automatically included in the vortex integral. But you still have a flat sheet of wake shading from the CO7. Because of the line vortex shading from the inboard and outboard of the along each strip. So if you have a co-planar wind tail configuration, both are modeled by CO7s, and then you have to line up the spanwise cut. Okay, if you don't line up the spanwise cut, for example, if you don't have a spanwise cut on the tail, then you have a control point located at this position. Then the line vortex from the wing will hit this control point, which create a singular AIC matrix. Then you may ask, if the wing and tail they are not coplanar and there's a gap between the wing and tail, do I have to follow this modeling restriction? The answer is that if the gap, the distance d, the width of each strip is w. If w is less than d, somehow then you can relax this modeling restriction. If the w is greater than d, then you have to follow this modeling restriction. Another case, you have two panels that are too close, and so you have a small gap d between two panels. The size of the panel is L, and if L is greater than D, and this may create an air conditioned AIC matrix. So this because the influence coefficient between two panels is in the order of 1 over R. R is the distance from the sending panel to the receiving panel. So to circumvent this problem, you have to divide this panel into many smaller panels. So the size, if the size of the smaller panel L is less than D, and then you can avoid this air conditioned AIC problem. And in supersonic flow, the free stream Mach number determines the region of influence. And the region of influence is defined by a Mach cone. The cone angle is equals to arcsine of 1 over Mach number. So when the Mach number increases, the cone angle becomes smaller. Okay, and if the cone angle, if the Mach cone intersect inside the panel, those panel is defined as a super inclined panel. And to circumvent this numerical problem associated with the super inclined panels in supersonic flow. A special treatment for the aerodynamic influence coefficient is introduced in ZONAIR. And so if typically you have a super inclined panel, is you put the panels on the winglet face on the engine face. So because the engine face usually it has a large inclination angle, so in supersonic flow you can easily encounter the so-called super inclined panel. So you have to, for those panels, you have to use the P-shell car. In the P-shell car, you define those panels are the super inclined panels. Then for the inlet panel, you specify the flow penetration condition, and so you allow the flow to penetrate into those panels. Then you can get a very good supersonic solutions. However, if you have a body with a wrong leading edge, and then you can encounter the super inclined panel on the nose of the body. In this case, you can use like a body 7 car. Inside the body 7 car, you can specify the radius of the nose of the body, and then we will use the exact Euler solution to replace the ZONAIR compute solution around the wrong leading edge of the body. Okay. The Mach-Cohn angle can be computed by arc sine of 1/Mach number. So for an aircraft at a high supersonic Mach number, if you placing the panel directly on the inlet face, that may give you super inclined panels. So we have to avoid the supersonic inclined panel by all means. So one way to do that is modeling the inlet by the cut-in panels can avoid the supersonic panel problem. Also, unlike the CFD method, the CFD method, they simulate the flow, but the panel solve the potential flow equation that can only be used to model the flow. This is to say, in order to establish a good panel model that can capture most of the physics of the flow, the user must understand the overall flow structure. For example, if you have a convolution something like this, in the real flow, the streamline will go above here, and inside the flow will have a vortex inside underneath the streamline. And but however, if you model use ZONAIR to model the exact surface, and then when the flow reach here, you will have a 90-degree turn that creates a very, very high velocity, thereby create a very, very low pressure region. So to circumvent this problem, you cannot use ZONAIR to model the exact surface. You want to place the ZONAIR panels on the streamline, and same as here. So you place the panels on the streamline. Also, another case, if you have a fuselage, and the fuselage ends with a point, and in the real flow, when the flow reaching toward the end of the body, and the flow generally separate before it reaches the end of the body. So if you model the exact surface of the body, this is an incorrect panel model, and so you have to truncate at the end of the body. So you leave a hole at the rear end of the body. Then you put a C-bar around this circle, and the C-bar will create a weak surface to simulate this separate flow condition. And another one is that you have a nozzle, you have a tailbone. If you model the exact surface, and you may have a problem, because when the flow reach here, you will have a 90-degree turn, and you will create very negative pressure region. So in this situation, you have to place the panel to cover up the upper and the lower side between the nozzle and the tailbone. So you guide the flow along those panels all over from this nozzle and tailbone region. And in addition, you put a C-bar around the tailbone section. Then the C-bar will create weak surface, so in order to have this closure condition. And another case is if you model the wing using the thick wing modeling, and then you model the wing tip as a flat panel. So the wing tip panel and the upper and lower surface of the wing has a 90 degrees. Then you place the C rod, two sets of C rods, one attached to the upper panel, one attached to the lower panel. So you have a two set of grid line here. Then you place one set of C rod around the upper grid, and another set of C rod along the lower grid. And also you have to define an infinite line vortex. Then if you have a C-bar along the wing trailing edge, and in the C-bar you have entry PA and PB, then you can specify non-zero PA here, for example. Then the C-bar will generate an infinite line vortex. So this is the correct modeling. However, because the angle here is 90 degree, when the flow roll up from the wing lower surface to the wing tip, it will go to a 90 degree turn. This 90 degree turn will generate a very high velocity and a very low pressure region. So to circumvent this problem, you have to model the wing tip by a wrong wing tip. So the flow, when the flow roll up from the lower surface to the wing tip, it will not go through this 90 degree turn. And then when the flow reaches the C rod, and the C rod can somehow stop the roll up of the flow, and so this is a correct modeling. Another case, if you have a wing tail configuration, and the wake from the wing generated by the C-bar along the trailing edge of the wing only partially intersect with the tail. So if you model both wing and tail by a thick wing model, so how do you set up a RBE2 grid? And then first you want to create a plan. This plan is the plan of the wake generated by the wing trailing edge. Then you find the intersection of this plan with the tail. Then you specify the RBE2 grid along here and along here. And this can circumvent the wake penetration problem. Why? Because you have the wake surface from the wing trailing edge penetrate into this portion of the tail. Then you specify the RBE2 around here, and RBE2 also create the wake surface. This wake surface also intersect with the tail. And however, the normal vector between this wing wake and this RBE2 wake are opposite. So those two wake influence inside the tail cancel out with each other. So the resulting modeling is like this. So you have the wing wake hit this line, and then inside the tail you have no wake, And then after that, you have RB2 C bar along those RB2 grid, and you will generate the wake surface. In so doing, and then you don't have this wake penetration problem. And so you have to define the RBE2, and along this side, also along those grid, and the location of those grid are the plane of the wing wake intersect with the tail, and so you define RB2 grids along this line, and then we can validate this approach. So we compare the ZONAIR solution with the Found 3D Navier-Stokes solution at Mach 0.6, angle at 3 degrees. This is upper surface CP, this is lower surface CP. You can see we can get a good comparison. And then we compare the CR with angle attack, CM with angle attack between the Found 3D and the ZONAIR solution. We can get a very good correlation. And for the supersonic Mach number at 1.7, angle attack 3 degrees. This is upper CB on ZONAIR model. This is a Found 3D Navier-Stokes solution. This is a lower surface. Again, we have a good correlation. This is a CR and CM comparison at Mach 1.7, angle attack from -3 to 6 degrees. And the computational time and this space is proportional and increase exponentially as the number of panel increases. So generally, we recommend that the number of panels be kept below 5,000. However, today's computer and today we release only the 64-bit ZONAIR code. So somehow you can increase this 5,000 this number to close to 10,000.